So recall we arrived to this bound for this term. So this was for several F inequalities. Recall that all F inequality told us that we have, if S is equal, then we have different cases. S greater than n over 2, S less than n over 2, and then we have in this case is 2 less than equal to q infinity. Then we have in this case 2 again, and this case was the one special, and it was 2 less than equal than q less than equal than 2n over n minus 2s, and this was for u normal q less than equal u hs. That's from where this and this other bounds came from. Okay, just changing the numbers, it will give this, and this for the case s less than 3 halves, because we are in n equals 3. We are in this case. Okay, so to finish this bound, now we will say that this is less than equal to a constant than u square hr uhs, where r will be the maximum of s minus 1 and 1 half. Okay, we will see that this r will be useful also for the other case. Okay, and then when we join both cases, this will make a lot more sense. Okay, so just to remember what we are really doing, we are bounding this term. Now we will consider first on the case where s is between 1 half and 3 halves, and now let's see the second case. Okay, so the second case will be for s greater than 3 halves. Okay, now we choose p1 equal to 6 and q1 equal to 3. Okay, this yields, okay, so recall we had in the beginning ds minus 2 u squared norm 6 in this case, and now the other term will be norm u 3. Okay, this will be bound by norm ds minus 1 u squared to u norm 3. This will be because we will use that f 6 is less than equal, well, this is a Sobolev inequality. Now we are in the case where s is greater than 3 halves, so q can be between 2 and infinity. In this case is 6, and so this will be f will be less than equal to hs, and if you remember, this is we use it in the other side, we can use it in this side also. If this is less than equal, then the f2. Okay, so now we will use Hilda to bound this by ds minus 1u. We separate this 2 times, and we take one of these outside. Now we will have now 2 of these norm 3. Okay, squared. Now for the next bound we will use this again. For this it is also 6, so we will obtain the norm dsu 2u 3 squared. just to clarify, when we make this step, when we apply folder, we call that this is a convolution, so you always can take one u absolute value out of the integral, okay, and in that way one can apply a held, okay. Okay, so this will be less than equal than within constants of UHS U squared HR. Recall R equal to the maximum S minus 1, 1.5. This HS is bounded by this. Okay, this is of the lemma 1, this bound. Okay, and we can use Sobolev here. Now we have that we are in the case where this can be applied. We are in S greater than 3/2, so in this case Q can be 3, okay, and this S is greater than 3/2, then we can have this R. If S is equal to 3/2, then 3/2 minus 1 will be 1/2, and it will be the last case, the other case, okay. So for the case where S is greater than 3/2, we obtain this. For the case where S was between 1/2 and 3/2, we have the same bound here, okay. So this bound, it will be useful for bounding this part, okay. So now we will go back here, what we wanted to bound, and let's put this bound and the bound that we got from both cases. So we got this, it will be less than equal than U squared H 1/2 U 2 plus U square HR UHS. This bound HRHS comes from, well, HSHR, we have this bound that came from both cases, here and here, and well, here have H1/2, we can replace this 1/2 by R, because it would be the maximum between 1/2 and R, so from there we will have this term. This bound comes from lemma 1, when we had JU minus JB, putting JB equal to 0, then we will have this result. Then lemma 1 will continue bounding this also, but we have this also, this bound, okay. So once again we can use that we have R, that is the maximum between 1/2 and x minus 1. Now we finally get the bound that we wanted, U squared HR UHS, okay. This will prove the lemma 3. So once we have the lemma 3, now we note that E minus ITA, okay, is a unitary group of operators. Okay, always recall A equal to multiplication n squared. This is a C0 group of isometries. Okay, but now on HS. Okay, so since the nonlinearity, okay, the convolution part, the Coulombian potential is locally Lipschitz, as we saw, Locality shifts continues from HS to itself. Then local well postness in HS follows similarly as explained in the proof of theorem 1 for H1 half. Okay, so now to show global well postness, we are going to use induction and this lemma 3, that an a priori bound on H1 half norm of solution implies uniform bounds on the HS norm on any compact interval, let's say 0 t star included in 0 t. Okay, so recall Duhamel's expression of the solution, so we can bound the solution in HS by E minus ITA norm HS plus 0 t integral norm E I minus IT tau, okay, this is tau, A if U tau is came from Duhamel's expression, okay, d tau, this will be less than equal than, here I forgot U naught, okay, this will be less than equal than U naught, okay, it's a unity, because this is a unitary group of freedom where you can bound, plus, and once again, a similar bound, if U tau, okay, HS d tau, and now we're going to use lemma 3. We'll say here we have a constant plus another constant, and now we can bound this by lemma 3 by U tau HS d tau, provided that UTH R is less than equal to 1 for R maximum is minus 1 1/2, okay, that's the next. Having this bound, we can invoke Grunwald inequality, and we will have that UT norm IHS is less than equal than E constant 32 T star, okay, the compact interval. For T in the compact interval, T star, including 0 T, okay. Don't forget that it's important to ask this so that we can use the bound, this bound, okay, this, we can take this as a constant and take the bound over HS. It is very important here, okay. Okay, so induction now implies that a priori bound that we can have in the case H1 half, that we already have it, guarantees uniform bounds on HS, okay, on any compact interval I included in 0t. So the maximal time of existence in HS, okay, coincides with the maximal time of existence in H1 half. So therefore we have the maximal time existence in HS values coincides with the maximal time in H1 half. Therefore sufficient conditions for global existence in H1 half valued solution imply global in time HS valued solution, okay. That means that we associate the local solutions in H1 half with HS, and we can, in that way, as in H1 half, we can extend T as much as we want. Then every solution associated with one in HS sloped solution. Now, by induction, we will have the global solutions for HS because of this association from H1 half to HS that we've got from the local and from this reasoning that we have, okay. That completes the proof for the theorem. that's 0.